Hey, geometry students, this is Mrs. Barnett. I am sorry that we're stuck at home, but we're going to learn anyway because that's what we do. I hope you have either the note taker printed because I linked it on Google Classroom, or you can just take notes on a lined piece of paper. Remember that this is a video, so if you need to pause it so you can write down everything you need to, you can. I'm going to go pretty quickly. All right, so pause it if you need to. All right, so we will be able to identify, make sure we have a pen, identify different types of symmetry in two-dimensional figures. So line symmetry is a certain one type of symmetry. It's a figure has line symmetry if a reflection over a line maps the figure onto itself. So if we had a triangle, and I'm like, this is an equilateral triangle, if we had this line, we could flip it over that reflection and it would land right back on top of itself. So that's what we're looking for. Will it land on top of itself? So state whether the figure has line symmetry, right? Yes or no. If so, draw all the lines of symmetry and state their number. So first, this is the trickiest one, probably this parallelogram that we're starting off with. Can we draw a line like down the middle, down on the diagonal, that would fold the line onto, or fold it onto itself, or flip it over the line so it landed right back on itself? Well, pause it, think about it. What do you think? All right, I'm going to assume that you paused it. The answer is no. If we do a line right down the middle like this, like this, is that going to map onto itself when we do the reflection? Let's talk about it. Let's say this is point A, B, C, and D. If we reflect those points over that line, A and B might be in this right spot. This could be A prime, and this could be B prime. But D prime is only going to end up like right here, and C prime is going to be way over here. This one, it would not map onto itself. And even if we did the diagonals, that too wouldn't map onto itself. I encourage you, like in class, I usually take a piece of paper that looks like a parallelogram and fold it and show you guys that it doesn't work. So try that. Cut out a parallelogram and fold it on top of itself. It doesn't work. Just kind of take my word. So the answer is no. This one does not have line symmetry. Does this 1, 2, 3, 4, 5 pentagon have line symmetry? Yes, it does, but I think there's only one line. We could draw this line right here down the middle. It would fold onto itself. So yes, one line of symmetry. All right, the rectangle. Think to yourselves, how many lines of symmetry are there? Can you draw them? Would they fold on top of each other? All right. Pause it. Try it. All right. I'm assuming you paused it. Okay. So there are two lines of symmetry. One of them goes like this, right down the middle. That looks right down the middle. And the other one goes like this. So yes, two lines of symmetry. Some people like to, I'm going to use a different color, try and do like a line of symmetry like this, like going from on the diagonals, but that would not fold on. Like if we did a reflection, this point right here is going to end up right here. If this was A, this is going to be A prime. It's not going to land on itself, right? We're going to have a rectangle that looks more, and if this was D, D prime is going to end up down here. It's not going to end up on itself. So that's an issue. All right. Okay. Next page. We're going to talk about rotational symmetry. So, rotational symmetry. A figure has rotational symmetry if, what's the if? If a rotation less than 360 degrees maps it onto itself. So 360 degrees would be a full circle. So we're looking for something that's less than a full circle to for it to rotate onto itself. So we rotate it a little bit and it maps right back onto itself. So the magnitude of symmetry is the smallest angle through which a figure can be rotated so it maps onto itself, and the order of symmetry is the number of times a figure can be mapped onto itself. The number of times a figure can be mapped onto itself. So we figure out order. The order is equal to the magnitude. Oh, sorry, not the magnitude. Eraser is equal to 360 degrees divided by the magnitude. Okay, so we're going to state whether these have rotational symmetry, and if so, we're going to locate the center of symmetry and state the magnitude of symmetry and the order of symmetry. Okay, so first of all, does this have rotational symmetry? If we started here, could I rotate it less than a circle so it maps onto itself? And the answer is yes. I could rotate this point over this way, and it would map onto itself. We could just rotate the whole figure. I wonder if I can do that. Nope. Okay. So rotate the whole figure. And how many times could we do that? We could do it once, twice, 3 times, 4 times, 5 times, 6 times. So the order of magnitude is going to be 6. And the magnitude is the angle. So to figure out that angle, how many times can we take it? We do 360, and we divide it by 6, and that is 60 degrees. So the magnitude is 60 degrees because we could rotate it 60 degrees and it would land back on itself. All right, now it's a square. Could we rotate the square less than 360 degrees so it lands back on itself? Pause it, try and figure out the magnitude and the order before I tell you the answer. All right, here we go. So we could rotate this one 4 times. We could go 1, 2, 3, 4. Rotate it 4 times. So that means the order is 4, and the magnitude, let's see, we do 360, we divide it by 4, that's going to be 90 degrees. So 90 degrees. These are the answers. All right, and lastly, this flag type one, could we rotate it so it lands on itself? And I think the answer is yes. We can rotate this one over here and then back one more time to land on itself. So that's 360 divided by 2, which is 180 degrees. So the magnitude is 180 degrees, and the order of this shape is 2. All right, last thing we're going to look at is some flowers. So can we state whether the flower appears to have rotational symmetry? So we're not looking for line symmetry. We're looking at see if it can rotate on itself. So write yes or no. If so, copy the flower and locate the center of symmetry and state the order and the magnitude of symmetry. So these flowers, they look pretty symmetrical or rotational to me. It looks like if I put points on here, because it's easier for me to think that way, I could rotate it 1, 2, 3, 4, 5 times in the circle, and it would land on itself. There's the center. That's the point it's rotating around. So we do 360 divided by 5, which is 72 degrees. So yes, this does have rotational symmetry. The magnitude is 72, and the order is 5. All right, I encourage you to think about this yellow and the purple flower. Do they have rotational symmetry? What would it be? Pause it, think about it, and then unpause it, and then I will give you the answers. All right. So this one, could I rotate it? I would like to think about these 3 points, and I think the answer is yes. I could rotate it 1, 2, 3 times. So 360 divided by 3 is going to give me 120 degrees. So yes, this has rotational symmetry. The magnitude is going to be 120 degrees, and the order is 3. Lastly, this one does not look like rotational symmetry. I couldn't rotate it this much and the flower end up on itself. So I'm going to say no, it does not have rotational symmetry. But what kind of symmetry does it have? Pause, think about it. All right, it's got line symmetry. I could draw a line right down the middle like this, and it could reflect right onto itself. All right, thank you. I hope you learned something. Today there's going to be an assignment on Google Classroom to test to see if you understood this. Not to test, but to give you guys some practice with this instead of doing a worksheet for homework. I hope you're having a good day. Let me know if you have any questions. Thank you. Bye.